Welcome to the class lecture on biomechanics, a crucial part of medical physics. I'm Dr. M. Balaji, Assistant Professor in the Department of Physics at Saurashtra College, Madurai, Tamil Nadu. Let's start by exploring the contributions of early biophysicists. Heraclitus and Epicurus laid the groundwork with their theories on life processes and atoms. Galen's medical research influenced Western medicine, while Vesalius's anatomy work set new standards. Leonardo da Vinci and Giovanni Alfonso Borelli further advanced our understanding of biomechanics. Luigi Galvani and Alessandro Volta were prominent Italian scientists who made significant contributions to bioelectrochemistry. Galvani's experiments with frog legs and electrical currents led to groundbreaking discoveries, while Volta invented the electric battery, revolutionizing the field. Galvani's experiments demonstrated that electrical currents could cause muscle contractions in frog legs. He used an electrostatic generator and Leyden jar to generate and store electricity, showing that direct contact with electrical sources was not necessary for muscle contraction. Volta built on Galvani's work by creating the first battery. He used two different metals and the sciatic nerve of a frog to generate an electric current, proving that electricity could be produced chemically. Volta's further experiments involved creating electric piles with dissimilar metals, demonstrating the generation of electric current. His work laid the foundation for modern batteries and electrical storage. Now, let's shift our focus to the physics parameters used in the respiratory system, specifically gas exchange and the regulation of breathing. Key factors include the diffusion of gases, partial pressure, solubility in liquids, and temperature. Diffusion is the movement of molecules from a high concentration to a low concentration. It occurs slowly over long distances but quickly over short distances, playing a crucial role in respiratory processes. According to Fick's law, the rate of diffusion depends on the diffusion coefficient, membrane area, and energy gradients. Gas exchange surfaces are typically thin with a large surface area to maximize efficiency. The total pressure exerted by a gas is related to the number of gas molecules and the volume of the chamber. The ideal gas law, PV equals nRT, helps us understand this relationship in respiratory systems. Air is a mixture of gases, each exerting its own partial pressure. Dalton's law states that the total pressure is the sum of these partial pressures, which is essential for understanding gas exchange in the lungs. The total pressure of air can be described as the sum of the major gases found in it. At zero humidity and sea level, the partial pressures of nitrogen, oxygen, carbon dioxide, and water vapor add up to the total atmospheric pressure. The solubility of gases in liquids is directly proportional to pressure, as described by Henry's law. This principle is crucial for understanding how gases dissolve in blood and other body fluids. Graham's law states that the diffusion rate of a gas is proportional to its solubility and inversely proportional to the square root of its molecular weight. This explains why oxygen diffuses faster than carbon dioxide in the body. The respiratory system is designed to circulate gases efficiently. It has a high surface area and is protected for breathing air, but it's not suitable for water. The upper and lower tracts play distinct roles in this process. The respiratory system operates through changes in pressure during inspiration and expiration. The diaphragm and intercostal muscles work together to facilitate the movement of air in and out of the lungs. Respiration involves several key processes: external respiration at the respiratory surface, internal respiration at the tissues, and mitochondrial respiration within cells. These processes ensure efficient gas exchange and energy production. The lower respiratory tract includes the larynx, trachea, bronchi, bronchioles, and alveoli. These structures work together to ensure efficient airflow and gas exchange in the lungs. Oxygen moves from the alveoli into the blood, while carbon dioxide moves from the tissues into the alveoli. These diffusion gradients are essential for maintaining proper respiratory function. The body consumes about 250 milliliters of oxygen per minute and produces 200 milliliters of carbon dioxide. The respiratory quotient, which is the ratio of carbon dioxide produced to oxygen consumed, averages around 0.8. Diffusion is a rapid process that takes about 0.25 seconds within the first 33% of the capillary length in the alveoli. Partial pressures of oxygen and carbon dioxide differ between the atmosphere and the alveoli, facilitating gas exchange. This process includes the exchange of gases between alveoli and capillaries, mixing of atmospheric air with alveolar air, and saturation of alveoli air with water vapor. Hemoglobin plays a crucial role in oxygen transport. At 100% saturation, 1 gram of hemoglobin carries 1.34 milliliters of oxygen. The average hemoglobin level in blood is 1217 gm per deciliter. The cardiac output is about 5 liters per minute, and tissues need 250 milliliters of oxygen per minute. In cases of anemia, tissues may not receive enough oxygen, leading to fatigue. Carbon monoxide is a dangerous byproduct of combustion that binds to hemoglobin with 250 times the affinity of oxygen. This can lead to hemoglobin being fully saturated with carbon monoxide at a partial pressure of 0.6 mm Hg, whereas it requires 600 mm Hg of oxygen to achieve the same saturation. High altitude ranges from 8,000 to over 18,000 feet, with extremely high altitudes reaching up to 29,000 feet, such as Mount Everest. The physiological challenges increase with altitude. As altitude increases, the pressure declines, reducing the partial pressure of oxygen. This means less oxygen is available per breath. At 12,000 feet, you receive about 40% less oxygen per breath compared to sea level. Thank you for your attention. We hope this presentation has provided valuable insights into the diffusion and solubility of gases, hemoglobin's role in oxygen transport, and the effects of altitude on oxygen availability.